So write a program to find the factorial of a number. Here we are trying to find the factorial of 3. So 3, we are moving it to the register R0, and then I'm moving the same value to R1 also. Now here what I'm doing, I keep subtracting 1 from the register, and I compare the content of register unequal. The same branch unequal to stop. Okay. So the moment it reaches 1, you have to stop. So you cannot go till 0. So and then if this condition you multiply with R1 and the result goes to R3. So next, this is your new updated result. So that result from R3 would we put it back to R0. Okay. So why can you people tell me why we are doing this? See, multiply R3, R0, R1. And again, the result which is there in R3, we are putting it back to 0, R0. Can you people tell me why we are doing so? Why? Hello? Please, you have to open mouth. Don't know? Am I audible?
Yes, sir.
Yes, yes, yes.
Oh, no, sir.
Yeah. So observe here, see 3 we are storing it and moving it to register R1 also. R0 also has 3, R1 also has 3. So when you're finding factorial of 3, when you want to find the factorial of 3, let me write here. So this is what you got to do, 3 into 2. Okay. So 3 into 2 is 6. Now we have 3 in R0 also and 3 in R1 also. Next, what I have to do? I have to multiply this 3 with 2. Now we are subtracting 1 from R1. R1 was how much? It was also 3. 3 minus 1 is 2. Okay. We have 2 in R1 right now. And now I'm comparing that 2 with 1. Okay. So 2 we are comparing with 1. So branch on equal to stop. Are they equal to? Is it equal to 1? No. So now the condition is false. It will not go to stop. Now we are here. Now what it will do? It will take the content of R0. R0 is still 3. Okay. And R1 is 2. 2 into 3 it will multiply. 2 into 3, 6. And that 6 goes to register R3. Okay. And from R3, we are again putting it back to R0. So my question is why we are doing this? From R3, why we are putting it back to R0? Say instead of this 3 factorial, let us take 5 factorial. 5 into 4 into 3 into 2. Okay. And this is 5. Let me write. Now what goes to R0? 5. And what goes to R1?
5.
What is the value that is moved to R1?
5. 5.
5. Next, what we are doing here? We're trying to subtract 1 because I need to get this 4. Okay. Trying to subtract 1 from R1. Okay. R0 is 5. R1 is also 5. 5 minus 1. Now in R1, it becomes how much? 4. Okay. Now this 4, I'm comparing with 1. So it does not equal. Now we come here. And then what we are doing? So R0, you have 5. 5 into R1. How much it is there? 4. 5 into 4, 20. And the 20 goes to register R3. Hope you people are following.
Yes.
Yes, sir.
Now this 20 which is in R3, you're moving it back to R0 again. Okay. So 20 goes to R0. So what was there earlier in R0? It was 5. Now the result of 4 into 5 is stored into R0. Now branch are not equal to fact. Okay, so we are again checking. Okay, so if these two are not same, okay, this is 4 and this is 1, they are not same, go back to the factorial. Okay, come back here and again subtract one more from R1. R1 was 4, now 4 minus 1 it becomes 3. Now again you're comparing 3 with 1, so they are not equal. Come here, what is there in R0 right now? Is it 5 or 20?
20.
20. 20 into 3 it is. Okay, 60. And that result goes to R3. From R3 again we are putting it back to R0. Now the kind of register R0 is 60. Earlier it was 20. Initially it was 5, and then got changed to 20, and now in the next iteration it is getting changed to 60. Now again you're comparing, branch are not equal to fact. So this is 3 and 2. Yes, they are not equal. Now you go back to the fact, and from 3 again you subtract one more. Now how much it is? 2. So compare 2 with 1. So they are not same. Come here. Next again, 60 into 2. So in R1 you have 2 now. This is 60. 60 into 2, 120. That goes to register R3. From R3 you're moving it to R0 again. R0 gets the value 120. Now branch are not equal. Yes, this is 2 and this is 1. Yes, they are not equal. Now go back to the fact. And then 2 minus 1, subtract. This is R2 is 2 minus 1, 1 it is. Compare. So R1 is 1 and this is 1. 1 and 1, they're same, they're equal. So jump on equal to 2, stop. What is the result now? 120. 120 factorial of 5 is 120. That is the result. And where is that found? In
R0.
R0. Now my question was, now can't you write mul instead of say taking the result to R3, from R3 putting again it back to R0, mul R0 comma R0 comma R1. Can't we write like that?
No, sir.
Why? Because I told, so in multiply instruction you cannot make use of the first source register as the destination register. You people remember, right? You said answer no?
Yes, sir.
Yeah, that means you remember that. So the first source register cannot be used as the destination register. Now R0 is my first source register, and if I change it to R0, it will not accept. I'll show you while executing what will happen if I make this R3 as R0, which is first source register. So it will not accept. Okay, so this is the program. You people understood. We'll go do this program in the Keil IDE and we will try to execute it.
Excuse me, sir.
Yes, ma'am.
Sir, why can't we write multiply R naught, comma R1, comma R naught?
R naught. Repeat again.
R1, comma R naught.
This is R1, this is R naught, and this is R1.
It's R naught, comma R1, comma R naught.
R naught, comma R1, comma R naught. Here R naught you are saying.
Yes, sir.
Yeah, that is possible. See, it is possible for you to make the second source register as the destination register, but not first source as the destination register. Following, right?
Yes, sir. Yes.
Second source register can be made as the destination register, but not the first source register. But I'm not using R1 here. I'm just again I'm taking a different register R3. From R3 I'm putting it back to R0. Okay, we'll execute it. Okay, so I'll open Keil IDE. Okay, so I'll go to new. Sorry, not here. Then close the project. Project. So inside this samples, I have a folder with the name lab. So this is what we created morning. Now I'll create one more. I'll go inside this, and then a project name also I'm giving it as lab 3. So startup.sh is not required. So now file new. I'll save this. So again, I'm saving this with lab3.s. So let me give the name of the program. Write the name of the program as assembly program 2. So when I write assembly, I have to write it as ARM assembly program 2. Find the factorial of a number. Now, so we'll start. So keep writing by yourself. So you'll learn, okay, the syntax and semantics, all these things. Don't try to copy paste area. So we'll give it as fact, comma code, comma read only. Okay. Now, so start and entry, all those things are not necessary. Let us directly start. Move. So R0, comma. So let us try to find the factorial of 5. So I'm moving 5. Then I want to move the same number to another register also, R1, comma R0. I'm moving the content of register R0 also to the R1. So next, what we got to do? What we got to do next? See, I have 5 in R0, 5 in R1 also. Now I need to do 5 into 4 into 3 into 2. Next, I need to get from this 5, I need to obtain 4. Now, how to get that? Sub R1, comma R1, comma 1, subtract 1. Okay. Now, after subtracting 1 from the content of register R1, what is the next thing you got to do? Hello? Okay, people are seeing my screen.
Yes.
Yeah, what is the next thing we got to do after subtracting 1?
Compare.
Compare and check whether R1 value is 1 or not. What is the instruction? Compare instruction? CMP R1, comma. Okay. You got to stop when R1 becomes 1. Compare R1 with 1. So then what is the next conditional statement? Yes.
BE.
If same, if equal, branch on equal, BEQ. Okay. So it's not like you have to write in uppercase only. You can write in lowercase also. So, but if you write in uppercase, it looks nice and neat. Okay, no problem. Okay. BEQ, branch on equal to stop. If the content at the moment the content of R1 register equals 1, so then say branch on equal to stop. So we'll write the stop. Okay, somewhere here, let me write stop, and then when it comes to stop, we got to say back the back. If it is not equal, then what we got to do? If they're not equal, if R1 is not equal to 1, what we got to do?
Multiply
Yes, multiply what and what?
R3, R1, R0.
Yes, we take a new register R3, comma R1, okay, R0, comma R1, okay. So this R0 is having your original value 5, and this R1 has the decremented value, that is 4. 4 into 5, and the 20 goes to register R3. Now after this, so 20 goes to the register R3, but I don't want it in register R3, I want it in the register R0. So move R0, comma R3. Okay, and then so again we got to do BNE, branch and not equal to where? Loop. Now how many times I got to repeat this? As long as the register, these two are not equal. Okay, so say R1 is 4 right now, and this is 1. 4 is not equal to 1. This is true, condition is true, loop back and perform this. Where it should go? Say the subtract should come inside the loop. So people understood? Is it clear?
Yes, sir.
Okay, and I'm not written, let me write now this yes suffix yes. Okay, so or it is not necessary also. Okay, let me not write first, and later we will try to add it. Okay, I'm saving this. So now we'll add this to the source group 1. Add file to the source group 1. So I've added. Now I'm going for translating it. Okay, sorry, end I'm missing. Excuse me for a while. Hello, sorry. Missing. And hello, if you're listening, right?
Yes, sir.
Yes, sir.
Hello.
Yes, sir.
No. Okay, thank you. Okay, so now I translate it again. So now 0 errors and 0 warnings. So build. Now we'll debug it. Okay. So we'll start. So this part will not touch because I've understood there are three things here: addresses, machine code, and then the mnemonic code. So this is what the mnemonic code for our understanding, and this is what the CPU understand. These are the addresses. Okay. So now we'll start from here. So putting the value of value 5, immediate number 5 to the register R0. And then same thing, we are moving it to the register R1 as well. So you can see here R0 and R1 have got the same thing. Now I'm trying to subtract. I'm subtracting 1 from the register R1. Let me expand this also. See PSR. So I'm subtracting 1 from the register R1. So now it is 4. Okay. So it is 4. Now I'm comparing this 4 with 1. Okay. So this compare will affect the conditional flags. So compare by default affects the condition flag. And that is the reason I removed this yes. Yes is not necessary here because we are using the compare, and this compare by default will always affect all the conditional flags. Okay. Now right now I compared and you can see the 0 flag is still 0. That means they are not equal. Okay. So branch on equal to stop. So if the condition is true, then it should go to the stop. Now the condition is false, then it will go for multiplying. Okay. So multiply the content of register R0 and then the content of register R1. Okay. 4 into 5, it is 20. 20 in hexadecimal is 1 4. 1 4. Okay. So because 16 is 1 0, 17 is 1 1, 18 is 1 2, and 19 is sorry, 16 is 1 0, 17 is 1 1, 18 is 1 2, 19 is 1 3, and 20 is 1 4. Okay. You should get 1 4 in the register R3. Here in the register R3, you should get it as 1 4. Okay. So we could have used R2 itself, but we have not used. We are using R3. Okay. No issues. Now, if I press F11, so R3, in R3 you should see 1 4. See, in R3 it is 1 4. Hexadecimal equivalent for the decimal 20. Next, we are putting this back to the register R0. Okay. So this is the intermediate result. Okay. And it is put back to the register R0. Now I'm checking branch are not equal. Now what this will check again? So this condition is different. Again, we are examining the 0 flag, but here I checked for the equality and here for not equality. So branch are not equal to loop. Yes. So 0 flag is 0. So this is true. As long as 0 flag is 0, this condition is true. As long as 0 flag is not 0, this condition is false here. Okay. Sorry. Yeah, this is false. For this condition it is true, and for this condition it is false. OP people understood? Hello? Please?
Yes, sir.
Okay. See, how much time you need to just unmute and say yes, sir, or no, sir? Okay. Now, don't make me to ask 2 or 3 times. Okay. Now loop back. So it goes back. Now subtract one more from R1. So how much it is? 3. Now you're comparing. See, R1 is 3. So comparing 3 with 1. Okay. And again, 3 is not equal to 1. 3 is not equal to 1. You don't have the 0 flag set. Okay. Internally, what this compare will do is, so the compare is also going to subtract the content of this from this. And when after subtraction, so then the subtraction result is not displayed anywhere. Okay. It does the subtraction operation in order to check whether they are same or not. Okay. Now when it does the subtract operation, if the result is 0, then it sets the 0 flag. So that is why. So it's not directly looking into the content of the register R1 and then the immediate number 1. What it will do, it will internally does the subtract operation. So OP people understood what I'm saying? Yes or no?
Yes. So,
Yes, sir.
yes.
See, there is nothing like directly looking into the register content and then saying they're equal or not equal. There's nothing like that. So it all goes with the subtract operation. Okay. Even the compare instruction internally does the subtract operation. It will try to subtract the value 1 from the register R1. If when the subtract operation is done, if the result is 0, then the 0 flag is set. Right now they are not equal. Again, this condition is false. So we are here and now multiplying 14 into 3, that is 20 into 3, that is 60. 60 in hexadecimal is how much? What is 60 in hexadecimal?
One zero.
10. So 14 into 3. So 3C you have to get. Okay, 3C is the result. Now in R3 now you should get 3C. So I'm pressing F11 now. See, 3C is the result. And now you put that back to R0. So R0 got 3C. Okay. Now branch are not equal. So again, it uses this. Now as long as this 0 flag is 0, it branches back to loop. Okay. Now this is 3 and this is 1. Yes, they are not equal. Okay. And it goes back. Now just by looking into the register content, we are saying yes, they are not equal, and we say it loop backs to the loop. But processor, so it will never look into the content of the register. What it will see is the 0 flag. Okay. Now yes, back, and now from R1 we are subtracting one more. So R1 is 3 right now, and 3 minus 1 is 2. Okay. Now this 2 compared with 1, 2 minus 1 is 1. It is the result is not 0. Again, this condition is false. BEQ to stop is false. Now multiply again. So 3C into 2 is okay. 3 is equal to 78 in hexadecimal. Okay. 78 is the hexadecimal value. If I press F11, so R3 register gets 78. So 78 is the value. Now put the 78 back to the register R0. So R0 got 78. Now again I'm saying branch are not equal. Yes, 0 flag is still 0. Okay, so they are not equal. This is 2 and this is 1. They are not equal. Loop back to loop. And then subtract one more from the register R1. R1 value right now is 2. 2 minus 1 is 1. So now the R1 content is 1. Now we are comparing. R1 is also 1 and the immediate number with which we are comparing is also 1. 1 minus 1 is 0. Now you observe the moment I press F11, the 0 flag, so it was still, so all this time it was 0. Now it will change to 1. Observe now. See, so compare 1 minus 1 is 0. The result of this compare operation is 0 and we have the 0 flag set. Now branch unequal to stop. Now this 0 flag is saying yes, the content of register R1 is same as the immediate number with which you are comparing. Now the condition is true, it comes to stop here. So we are in stop right now and then back be back. Okay, it keeps looping here itself. Now our result is there in register R0. What is our result? 78. So this is in what hexadecimal, and the decimal equivalent of 78 is 120. Okay, you can just find out here. Okay, so I just clicked on hexadecimal, it is 78. So and I click on decimal, it is 120. Hope people understood. Hello.
Yes, sir.
Yes, sir.
Yeah. Please, your voice breaked, man. It's breaking. I was not able to hear you properly. Hello.
Yes, sir.
Followed, right, everyone?
Yes, sir.
Yes, sir.
Okay. Now, so let me start debugging. Okay. Now let me add this suffix yes. I said it is not necessary. So we executed the program even without the suffix s because the compare itself is doing that. Compare by default will always update the carry flag. Sorry, conditional flags. So even if you put the suffix s, nothing is going to happen. So now we have two instructions affecting the conditional flags now. Sub s also affects the conditional flag. Even the compare is also going to affect the conditional flags. And that is not necessary. Why we need to trouble two instructions to affect the conditional flags? So when compare it alone can do it. Okay. So unnecessarily we are troubling the processor now by making the processor update the conditional flags through two instructions. So which is not really necessary. Now I did the changes now to this my source program. Now I got to retranslate it again. So I translated it, building it. So now I'm going for debugging. Okay. Now before I start, let me expand this. PSR. See, there's something. Uh, I don't know. Operating system. Yes, you said you're studying this concept called one process to the another process is so rapid, so you get a feeling that all the processes are getting executed simultaneously. Now, but so that is not happening. So what's happening is CPU switching from one process to the another process. All the intermediate results of the process which was executing, will be saved on PCB. And what is it? So the entire register content. So, for example, execution of the second program for some amount, and then so it wants to switch back to the first program which it was earlier executing. Now, before switching back, so the state information of the process which was executing earlier will be reloaded from the PCB to the registers. OP people are understanding what I'm saying. There are a lot of things. So all these things are connected. This is connected to your operating system as well. You understood what I told? Hello. Hello.
Sir, could you repeat,
Yes,
sir?
sir.
You want me to repeat? So I feel
Yes,
this
sir.
is important. I'll just show you because very important. 1 second. Let me open a blank PPT because if I don't write, it'll not follow. Uh, so let me open a blank PPT. I guess I have. New. Okay. Okay. So first answer me. Say assume within a system you have. Assume this is a system. Your system. Your computer system. So assume on this system right now, we have the process P1, process P2, process P3 are running. Hope people are following. And I have one CPU. Okay, there is one CPU. Okay, and these are the three processes which are currently running. Okay, now what CPU will do is, say it's not like it will take one process and it will execute this process till its completion. So what CPU does, it say starts executing with the process P1. It performs the execution of process P1 say for 1 milliseconds or 2 milliseconds, and then stops the execution of P1, switches to P2, because fair chance should be given for all the processes which are running. Okay, so if CPU says no, I cannot switch and execute all the processes. I'll take one process and I'll execute it till its completion. It would have been not possible for you to do multiple things simultaneously on the computer system. But we are all doing it, correct? So so when I'm typing something in my WordPad or Notepad, I simultaneously keep listening to the songs. Correct? No, I can open my Winamp and play a song, or I can play a video. Correct? No, or I can do many things. So there are a lot of things which we feel like they're simultaneously happening. So, but they're not happening simultaneously. If you have multiple core processor, then all of them will be happening simultaneously. If I assume there is only one CPU, this CPU can execute all these processes by switching so rapidly between them. Say the CPU takes process P1 for executing first, and it performs the execution of the process P1 say in nanoseconds range, so 1 nanosecond or 2 nanoseconds, and then immediately switches to the process P2, performs the execution of P2 for another 2 nanoseconds or 3 nanoseconds, and then switches to P3, performs the execution for 1 or 2 nanoseconds, and then immediately switch back to the process P1. So all of them will be executed. So by using the concept of switching. Okay, say the process CPU right now is executing the P1. Okay, and when P1 is under execution, this program or process is under execution. So all the registers which we were discussing now, R0 to R15 and CPSR, will be filled in with the content of what? With the data which is related to this process. Yes or no?
Yes, sir.
Correct. So when I say this process is executing, okay, and CPU, this CPU is allocated to this process and this process is under execution, all the register R0 to R, I don't have a separate register for this process and separate register for this process and separate register set for this process. It is the same common registers which will be used by all of these processes. So when this process is under execution, so it will be using all the registers R0 to R15 and CPSR and SPSR, everything. So now when the CPU wants to stop the execution of P1 and switch, so this is not yet complete. So it's only stopping it intermediately. Okay, stop the execution of P1. Say so the total time required for executing this is say around 10 milliseconds. So 10 milliseconds of execution time is required. Among this 10 milliseconds, this process P1 is executed only 2 milliseconds. So still the process P1 has to continue its execution for 8 more milliseconds. And before that, the CPU switched and it is made to execute the process P2. Now all the results, intermediate results of the process P1 which were there in the registers R0 to R15, what you got to do? You got to save it. Now without saving or backupping, so if you allow the CPU to simply perform the execution of P2, what will happen? So the P2 is going to overwrite the content of all the registers R0 to R15, and the execution what this process P1 was made till now, so it will go waste. Okay, so that is all the content is taken and it is saved into something called as PCB, process control block. It's a data structure actually. So data structure subject we have studied the previous semester. So this is a data structure. So PCB, every process has its own data structure called as process control block. So when before contents of this registers is copied and then they are stored into the PCB of the process one. Let me write it as PCB1, and then the CPU switch to allow to execute the process P2. Okay, and say Even this process P2 is executed for some amount of time and the CPU wants to go back and resume the execution of process P1. What will happen again? So the content of the register R0 to R15, which was written by the process P2, will be backed up to its PCB, that is PCB1. It is another data structure, PCB2. PCB2. Now when CPU switches back to this, what it will do? It will resume. It will go to its PCB associated with this process P1. All the status information or the intermediate results which are here, they'll be reloaded into the registers, and then the CPU will continue its execution. Hope you understood this.
Yes, sir.
You understood what I mean to say, right? So just we'll study an operating system again. Okay, so this is something called as context switching, CPU context switching, and so you'll understand there in detail. Now, when I mean to say the context information is being saved onto the PCB process control block, what does that? It does nothing but so saving the content of all these registers. These are all the CPU registers, saving the content of all these registers to the PCB associated with the process. Okay, and when the process is about to resume its execution again, the same status information which is available inside the PCB will be loaded into the registers. Got the point? Hello? Hello?
Yes, sir.
Okay. So now we are with yes, we are executing just to see that. So this doesn't have any effect because compare is already doing that. But on top of that, again, if you write yes, so it is only a burden that we are putting on the processor, nothing else. Okay. It gives you the same result. So 5 is moved to register R0. R1 also got 5. Now sub S. Okay. R1 minus 1. That is 5 minus 1, 4. So I see even sub S is able to affect the conditional flag, and the same thing will be done by the compare also. Okay. Next, BEQ, so not equal. So then multiply, again subtract. You can see I'm just going too fast. Okay, now see, so this subtracted. Okay, so but this was not able to update the 0 flag. So because here 2 minus 1, it becomes 1. It is the result is not 0, but this is going to do 1 minus 1 and the result becomes 0 and it is updating the 0 flag. And this adding suffix yes is not necessary when you have the compare statement. Hope you people understood. Please.
Yes, sir.
Okay.
Yes,
Now this
sir.
is not necessary. So in the manual it is there, but it is not necessary. You can remove that. Next, one more thing that I wanted to show you people is this. So you cannot have, say, whenever someone looks here, it feels and they feel that we are doing some kind of a donkey work here. So you're multiplying, okay, you add the result in R3 and from R3 again you're putting it to R0. So we are not doing a donkey work here. So we know that the multiply instruction, you cannot make the first source register as the destination register. That is why we have written here something like this. Now let me comment this statement. And now instead of this R3, we'll put directly 0 here. Okay, and we will try to run. So I'm translating. Okay, so now you can see here. So it's an error. This register combination results in an unpredictable behavior. Okay, so what register combination? You're trying to make your first source register as the destination register, and this register combination, that is using the first source register as the destination register, will result you with the unpredictable results, and that is the reason it is not allowing you. Even your translator, the assembler itself has detected this and it is not allowing you to proceed further. Okay, this is fine. Now is it possible for me to use the first source register as the destination register? Yes, it is possible. Okay, now let me save. Okay, now I'm translating it. See, 0 errors and 0 warnings. But this will not help me in any way. Okay, so R0, what do you mean to say? Yeah, you can, yeah, so that way you can do. I think one of the student asked me. So R1, so here you make it as R1 and this is R0, and then you can use R0 over here. Hope you people understood?
Yes, sir.
Okay, so this is about this lab program number 3. So I guess you have understood it in depth. Okay, and so even if I ask you people to write without seeing, I guess you people will write this program without seeing, and a lot of things you have already understood. So again in the module 2, so each of the instructions you're going to understand in depth. Every instruction you'll study there. Okay, so but this is just for the sake of explaining the lab program purpose. I've told you what each of this instruction is and what they are doing at the eye level. But we discuss these things in more detail in the module 2. So okay, let me correct it, bring it to the original form. So R3, comma R0, comma R1, and this I need to uncomment. Let me save this. Yeah, hope all of you copied this. All of you copied.
Yes, sir.
Yes.
Okay. See the programs. So like this, I think the fourth program also it's a simple program like this, and after the fourth onwards, all programs are with some amount of thing to understand with those programs. Okay, here also, even though the program looks very simple, so there is which you need to understand behind these programs. Okay, so the fourth one, the lab program number 4, is again a simple one. So why I just started with the 2 lab programs today itself was to give you a brief idea before I go to the further topics. So before I enter into the second module. Okay, so soon, I think after another 2 to 3 classes, I'll be getting into the module 2. So there, before I get into the module 2, if you have the experience of for doing some programs using the instructions, so I feel you'll get mm, more comfortable in understanding the module 2. So with that intention, so I have in depth covered the lab program 2 and then the lab program 3. Okay. Uh, so if you have anything to discuss with me, please feel free to discuss. See, whenever you're studying or it may be computer organization you've already studied. So any other subject, when you're studying, so please try to relate everything. So this is what the one point which I wanted to highlight you people. So that is the process control block. Whenever you say the process CPU is switching from one process to the another process, all the current context of the process will be saved into its PCB. This is what you study. This is a statement that you study in the operating system. What that really means is this: all the contents of the CPU registers will be saved into the PCB, and then the CPU is allowed to switch to the execution of the next process. Okay. And when the CPU is about to resume back the execution of the previously executing program, it will again reload the status which is there inside the PCB of that process to the CPU registers and continues the execution. Okay, so all are something like interconnected. So um, so focus should be there. If you focus more, you understand in depth and your knowledge will grow. So let me discuss 1 or 2 minutes with you people. So by randomly calling some numbers. 52. So please unmute. USN phi 2. USN phi 2. Okay. Oh, let me stop recording. So I don't want this to get recorded.